In this video, we're going to discuss a sample problem that's related to static equilibrium. This is Physics is Easy with Mr. Jesse. So here is the problem. If W is equal to 40.0 Newton in the equilibrium situation shown in the figure below, find T1 and T2. Now in this example, T1 and T2 would be different mainly because of the fact that the angle that are associated with these tension are different. So that means our T1 and T2, you should expect it to be of different values. In fact, we are already given that T1 is 58.3 newtons, whereas T2 is 31.0 newtons. So to arrive at this answer, the first thing that we need to do is to be able to determine the free body diagram of the setup, or identify the forces that are involved in this particular situation. And once we are able to identify the forces, then we identify the components. So here is the free body diagram. So at this point, we have the forces T1 pointing along the direction of the rope and pointing away from this position. So this is our T1. Our T2 should also be drawn along the rope, and it points away from the point of intersection. So at this point here, that's our T2. And also there is the weight of the hanging object that points downward, and we call that W. All right, now T1 will have the following components: T1y, which is the y component of T1, and T1x, or the x component of T1. We are also given the angle here, which is 60 degrees, and by virtue of alternate interior angles, this part here is also 60. On the other hand, for T2, we have here our T2x, or the x component of T2, and T2y pointing downward, or the y component of T2. So if you notice, T2 is actually pulling towards this direction, and of course you should be able to intuitively determine that T2y is a component that points downward. Now if this is 70 degrees here, then therefore this small angle that we have here should be 20 degrees, because this part here actually forms a right angle, and we know that a right angle will have a measurement of 90. So if this is 70 right here, the other part should be 20. Now that we have identified the forces involved as well as their components, it is very important to set up our equilibrium equation. So let's begin with the sum of the forces on the x-axis. So this is how we write it. Sum of the forces on the x-axis, that should be equal to 0, because there are no forces, or there is no motion along the x-axis, or no acceleration along the x-axis. In fact, the object is just in equilibrium or static equilibrium. Then the sum of the forces on the x-axis should be 0. And what are those forces on the x-axis? We have negative T1x plus T2x is equal to 0. Now why is it that T1x is negative and T2x is positive? So it has something to do with their direction. Since T1x points towards the left, that should be negative by convention, and T2x, which is the component of the force that points towards the right, then we will designate it with a positive value. That is our first equation. Now we also set up our equation for the y-axis. So the sum of the forces on the y-axis, and that should also be equated to 0, because there is no motion along the y-axis. And what are those forces along the y-axis? So we have T1y, that should be positive because it points upward. On the other hand, our T2y, or the y component of T2, points downward, so we will have negative T2y as well as negative W because this force here points downward. So we will have minus W is equal to 0. Next, we will identify, or we will express T1x, T2x, T1y, and T2y in terms of T1 and the angle and T2 and the angle respectively. So looking at T1, if this is our T1x and this is the angle that we are dealing with, so this side here is actually adjacent with respect to this angle 60 degrees. So by virtue of SOHCAHTOA, we can say that cosine of the angle is equal to the adjacent side over the hypotenuse, and our angle would be equal to 60 degrees. That's cosine of 60 degrees is equal to the adjacent side of that 60 degrees is our T1x. So we will have T1x divided by the hypotenuse. In this case, that is our T1. So that will be T1. Hence, our T1x is just equal to T1 cosine of 60 degrees. On the other hand, our T1y is opposite to this angle 60 degrees. So we could also draw T1y on this side. We could actually draw it here also. So this is also T1y. So if you notice, this T1y is actually the same as that T1y right there, and T1y is a side that is opposite to the angle 60 degrees. So the function that we're going to utilize is the sine function, which says sine theta is equal to opposite over the hypotenuse, and our theta is 60 degrees, so sine of 60 degrees is equal to the opposite side, once again, is our T1y. So we will have T1y divided by the hypotenuse, which is our T1. Then we could say that our T1y is just equal to T1 sine of 60 degrees. Whereas our T1x is T1 cosine of 60 degrees. Now, moving to the other side of the rope. So here we have our T2 with its components T2x and T2y. So if we are going to consider this angle here, 20 degrees, then we can say that our T2x is an angle that is adjacent to this 20 degrees. So similarly, we could just say T2x is equal to T2 cosine of 20 degrees. Whereas our T2y, which is the side that is opposite to the angle of 20 degrees, then we could say T2y is equal to T2 sine of 20 degrees. However, if the angle that we would utilize is the 70 degrees, notice that 70 degrees is actually the same as this angle right here. This is 70 degrees. And by virtue of alternate interior angles, so these are actually alternate interior angles, they should be equal. So if we would utilize the 70 degrees, you would notice that Ty or T2y is now the side that is adjacent to the angle 70 degrees. So since T2y is adjacent to 70 degrees, then we could also say that T2y is also equal to T2. Since it's the adjacent side of 70 degrees, then we say cosine of 70 degrees. So that's T2y. On the other hand, if we are using our 70 degrees as the angle of reference. Our T2x is the side that is opposite to this angle 70 degrees. So it's the opposite side. So we would use the sine function by virtue of SOHCAHTOA. So we would say that T2x is also equal to T2 sine of 70 degrees. Okay, so now let us substitute to the equation that we have here at the bottom. So we'll have negative T1x is T1 cosine 60 degrees plus T2x. So we came up with T2x having two possible values. So it's up to you what you're gonna use. You could use this or this. So I'll use T2 cosine of 20 degrees is equal to 0. And that is my the summation of the forces on the x-axis. For the y-axis, so we have T1y, so that's going to be T1 sine of 60 degrees minus T2y. So I'll use this value, T2y, T2 sine of 20 degrees. But again, you could also use T2 cosine of 70, it doesn't actually matter. T2 sine of 20 degrees minus, we are given the weight to be 40 newtons. So we have the weight right there. So if the mass was given instead of the weight, then we could just multiply the mass by acceleration due to gravity g, 9.8, then we will have the weight. Since the weight is already given, we just have to substitute it with 40 newtons, and that is equal to 0. And the rest is just mathematics. So having said that, as you manipulate, as you solve this problem, you have two equations with two unknowns. So you should be able to come up with this answer. T1 is equal to 58.3 newtons and T2 is equal to 31.0 newton. And that's the end of this tutorial. Always remember, physics is easy with Mr. Jesse.